Hello everybody! So in this video we are going to be talking about error bounds, not specifically just alternating series, but error bounds. So all that means, this can be called the tolerance. Essentially, tolerance is how much we are allowed to be off by. So the whole deal that we've been doing up to this point is we've been doing a bunch of tests and testing whether series converge or diverge. But the whole goal of series essentially is to find the sum, right? To actually figure out what it is. So just to show you, sine of x, right, that is odd. So I need to have x minus x cubed over 3 factorial. And I'm just going to go to those two units, or to the first two terms. If I want to estimate sine of 0.3, that will give me, hang on just one second, 0.2955. And if I actually type in sine of 0.3, the actual answer, right, this is an approximation, the answer is 0.29552020, blah, 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 right? So really, I was only off by 0.0002, and that is only going to the third degree polynomial. The error bound is going to come in saying, well, this error, or this guess, this estimate, is only off by a certain amount. That is where the error is going to come in. Because we won't always be able to use a calculator that has it probably to like the, I don't know, first 10 terms of sine or something like that. Maybe more, I don't know. I should look it up and know. But we're not always going to be able to use that to figure out what we are actually off by. So the first type of alternating, or the error bound that we will look at, is the alternating series. So an alternating series, right, let's say we look at, well no, I'm going to look at my first series here. 1 over n factorial. This is alternating because I have negative 1 to the n plus 1. That tells me it is alternating. It's going back and forth. This series is equal to 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6 plus 1 over 7, so on and so forth, right? I'm going a few because of the directions. I know the directions off the top of my head. Blah, 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 right? This is what it actually is. Now, if I wanted to estimate this, right, so approximate the sum of the series by using its first 6 terms. So the sum of the first 6 terms here is going to come out as 0.63194444444444 forever. That is what the sum of the first 6 terms are. Now, determine the bounds of the sum. Sometimes they say this, sometimes they don't. But if you're actually trying to approximate the sum, what we will do is also give a tolerance level. So if an architecture person comes to you as an engineer and says, hey, I need an estimate for this, you will also give them a tolerance level. So how much you could be off by in either direction. So now, thinking about alternating series, I went up to the 6th term. And then there's more terms beyond this. These are my remainders. Now, the remainder, if I think about these terms, I have 1 over 7 factorial, and then I'm going to take out a little bit, and then I'll add a little bit more back, and then take out a little bit more, add a little bit more back, take out a little bit more. But it will never get up to a full 1 over 7 factorial. So what I can say is that the remainder is less than or equal to the next term, the absolute value of the next term, right? And we do the absolute value just in case it was like a negative number. But I know this sum, the actual sum, is s sub 6 minus a sub 7. It's bigger than that, and it is somewhere less than the actual sum minus, or plus a sub 7. So if I find what a sub 7 is, so 1 over 7 factorial, and I'm going to Okay, so I've done those two calculations. So I'm somewhere between 0.631746 sum and 0.632142 blah, 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 blah. So what are these off by? They're off by the 7th term, and the 7th term is 0.00019412 blah, 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 blah. Right? So my error is no more off than this term. My sum has to be somewhere between the approximation of the first 6 minus and the approximation of the first 6 plus that next term. Because that next term is the biggest magnitude, because then I'll take out some, I'll add some, take out some, add some, take out some, add some. So essentially, going back up here, as long as I converge by the alternating series test, then the sum, the actual sum, minus the sum of the first n terms is no greater than, right, that difference, that error, right? So a lot of times I will just say error, that error is no more than the next term. So if I go up to 7 terms, then it's no more than the 8th term. If I go up to 12 terms, then it's no more than the 13th term off. That's all it's talking about when we are determining the bounds of the sum. If it says the approximation of the error, that is our error bound right there. Okay, moving on. Determine the number of terms required to approximate the sum of the series with an error of less than 0.001. Well, my error has to be no more than the absolute value of the next term. So that absolute value, this is alternating, it does converge, the limit goes to 0. So the error has to be less than 1 over n plus 1 to the 4th, and my error needs to be less than 0.001. So if I figure out where it is equal to 0.001, I wanted that to be equals. So let's see, if I go in and I figure out what that is, that comes out as 4.6234. So what that means is I must go to 5 terms such that my error is less than this 0.001 value. And that's it. That's all they're looking for here. All right, so the next thing that we are going to get into is into Taylor polynomials things. So let me just remind you that a Taylor polynomial is f of c plus f prime of c x minus c plus f double prime of c x minus c squared over 2 factorial plus f triple prime of c x minus c to the 3rd over 3 factorial plus blah, 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 blah. And Taylor realized that, hey, wherever I stop, if I stop somewhere, there must be some remainder. And I can find this remainder, this exact remainder for some value, whatever I'm trying to approximate, if I do the next derivative. The weird thing here is it is at some value z, but the next derivative would be x minus c to the n plus 1 over n plus 1 factorial. Now he said this value of z, this is something that I don't know how to find, is what he said. So I know this has to be the case because it has to be. No matter where I stop, I should be able to add something to it to get an exact result. Now, what that number is, I don't know, but I know I should be able to use this formula kind of for the next term, right? Just like I've been doing, the pattern is going to stay the same. So this will stay the same, but what number I multiply it by will be related to the next derivative but I don't know how to find this value of z, the y value for which I would have to multiply this by to get an exact remainder or an exact error. So I don't know what to do, but this is what I think. These are his thoughts. Then this guy named Lagrange, I don't remember his first name, but he came along and he said, hey, Taylor, that's a great idea, man. The cool thing about this that I think is that if I take your formula and I say that if I do the maximum value of that derivative, the maximum value, then the remainder has to be less than that. So I can give at least, I can tell you an error bound. I can say that your number is somewhere between these, and then Taylor's like, hey, that's really smart, dude. Yeah, that's cool. So I don't know that these two actually work together. I'm just making up that story to make it make sense. Anyways, but this is called the Lagrange error bound, where we are still using the first unused term, right? The n plus 1 factorial. And then I'm going to take the maximum value of that next derivative and multiply it by the next part of that. So let's take a look at how this is used. Again, here's your formula for it. The remainder has to be less than or equal to this value. Notice this is absolute value in case it comes out negative. This is also absolute value. The z is something that we are not going to be able to find. As far as my understanding, we do not know how to find it in mathematics quite yet. So again, we're not actually finding the x0, we are just bounding it. We will still use the first unused term, and we will often overestimate this error bound. So like if the fifth derivative was a cosine function, then the maximum of a cosine would be 1. So maybe I could use 1 in this place right here. Different situations will call for different things. All right, so let's take a look at this one. The function f has derivatives of all orders, so that just means I can find a Taylor polynomial for it, for all real values of x. Let p sub n represent the nth Taylor polynomial for f at x equals 1. So what they are telling us right here is that my center is 1. Show that the difference between the actual and the third approximation at 1/2 is less than 1/12. So they're essentially saying, right, this is the error is less than 1/12 at x equals 1/2, because that's what we're trying to find. They're evaluating f of 1/2 and they're approximating f of 1/2. So I'm going to say that the error must be less than or equal to x minus c, so 1/2 minus c, which is 1. Again, that is an absolute value, to the what power? Well, n plus 1, the next unused term, since this is a third degree polynomial, the first unused term will be the fourth degree. So over 4 factorial times the maximum of my fourth derivative. Well, how do I find the fourth derivative if they don't give me any information? But wait a minute, they do. So the maximum, this is my fourth derivative. This is the absolute value of my fourth derivative. And it looks like the maximum, especially on the interval from 1/2 to 1, but definitely the maximum for the entire function, maybe that is 28, maybe it's 29, I'm not sure, but I hope you agree in the fact that it is, I'm not going to draw a straight line, it is less than 30. The absolute maximum this could possibly be is 30. Everything is less than that. So what if I multiply this by 30 for that very reason? So the error should be less than 1 over 2 to the 4th times 4 factorial times 30. Let's do some simplifications. Over 16, 4 times 3 times 2 is 24. 30 over 24 will reduce to, let's see, divided by 6, 5 over 4. So this will equal 5 over 4 times 16 is 64, which is indeed less than 1/12, which is what we were trying to show. Because if I multiply 1/12, if I just multiply that by 5, then this is 5 over 60, which this is a smaller number because it has a larger denominator. This is all the work that they would be looking for on this problem. So I have shown, using the Lagrange error-bound formula, that the error is actually less than 1/12. I'm sure if we would have used 29 or 28, then it probably would have been an even less number here. But the issue, and this is going to be maybe hard for you guys at first, but you will often overestimate the error bound, right? So I don't know if that's hitting at 28 or 29. Could be 29.5. Could just be a really bad graph. I don't know. But for sure it is less than 30. We'll be able to look for one here in a second. I think it's the last one we're going to look at where we can actually find like the maximum value, and we'll use a calculator to do that. All right, I'm going to take a look at the next one here. Let f be a function that has derivative as all orders, and again, it's just meaning it's Taylor polynomial. But P sub 3 is the third Taylor polynomial before f about x equals 0. So that means my center is 0. So that means for me, this is really a Maclaurin. But I'll still use Lagrange error bound the same. It just means my center is 0. Converges at x equals 1, and this for this and all values of x of the following, which is the smallest value of case, which the Lagrange error both guarantees that the difference or the error is less than or equal to k. Well, my error formula is less than or equal to, again, x minus c, so x in this case is 1, minus c, which is 0, to the fourth power, since it is the n plus 1, over 4 factorial, and then I need to multiply by the max. The max of the fourth derivative. So let's take a look. Right? They tell me that my fourth derivative value, or my nth derivative value for n is between 1 and 4, the nth derivative value is less than this expression. So the fourth derivative has to be less than 4 over 5. That's what I'm going to use as my maximum value. So 4 over 5, which will simplify to 1 over 4 factorial times 4 over 5, and that is option B. They don't even simplify anything. Right? We could have also written this as 1 over 5 times 3 factorial, which would be 1 over 30 if we simplified. All right, last one down here. Function as f, blah, 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 blah. I'm given the fourth derivative is this. Third degree Taylor polynomial about x equals 0, so still a Maclaurin, is used to approximate f on the interval 0 to 1. What is the Lagrange error bound for the maximum error bound for the maximum error on this interval? So the error is going to be less than, well, my center is 0. So I have minus 0. I know I'm going to be to the fourth power since it is a third degree polynomial. And I'm going to the max of the fourth derivative of x. Now what is the value that I put in here? Right? This should be x. This should be where I'm approximating. And if I am centered at 0, my maximum error is going to happen when I am the maximum distance away from 0. Since 1 is the furthest right that I can go for this interval, 1 should be the place that I have the maximum amount of error. So I'll use 1 as my x value. Now for the maximum, what I told you earlier was that often for sine we will use 1. The maximum of sine is 1, so we'll just put in 1. And I think this is the way that your book does it. So the error, if I use 1 over 4 factorial times e to the first power, this comes out as 0.11326. However, that's an issue for this one because that is not actually the solution. So be mindful on what our interval is, especially when they give you an interval, they are using 0 to 1. Sine is not going to be a maximum of 1 on the interval from 0 to 1 because sine starts at 0 and doesn't hit that peak at 1 until pi over 2. And pi over 2 is 1.57. So what we actually need to do here is instead of using 1, use what sine is at 1. When we do this, again, make sure you're on radians, that will produce the correct answer, which is 0.0967, which will round to option B there. So just be careful. Think about your interval. Think about what the maximum actually is on that interval. But if it went from like 0 to pi or something like that, then yeah, sine could have been a maximum of 1, which would mean E would have been our maximum value there. So just take a look, think about what your maximum could possibly be. This case, it is e to the sine of 1. The last case, it was what they told us it would be. In the case before, it was based on the graph, it has to be less than the highest value that we see it approaching, essentially. So that's going to be kind of the frustrating part for you. That will be difficult to get used to and difficult in any situation. But how much do we overestimate that error bound? But as we go, we'll take a look at these things, and hopefully you'll start to see patterns in them and see how they work with the AP testing situation. All right, talk to you all soon. Well, bye!